the quiet corridors of NASA's Johnson Space Center, behind doors marked for authorized personnel only, a series of briefings have taken place over the past 3 years. Briefings that paint a very different picture of Mars colonization than the one we see in press conferences and SpaceX live streams. Documents circulated among senior planetary scientists, physicians, and mission architects reveal a timeline not of triumphant human settlement in the 2030s or 2040s, but something far more distant. Something measured not in decades, but in generations. Tonight, we explore why the dream of Mars, so vivid in our collective imagination, may already be revealing cracks that run deeper than anyone publicly admits. Mars has captivated us like no other world. The red planet hangs in our night sky as both promise and challenge, a rust-colored beacon calling to something ancient in the human spirit. For over a century, we have told stories about Mars, canals and civilizations, explorers and settlers, terraforming and transformation. In recent years, that dream has grown louder, more urgent, more seemingly within reach. Multiple space agencies have announced Mars programs. Private companies have revealed timelines. Billionaires have promised cities. The cultural momentum is undeniable. We are, by all appearances, racing toward Mars. Yet beneath this wave of enthusiasm lies a quieter current, one that flows through research labs and medical studies, through engineering simulations and psychological assessments. A growing body of evidence that suggests Mars is not simply difficult to reach or expensive to colonize. It may be fundamentally, perhaps insurmountably, hostile to long-term human habitation in ways we are only beginning to understand. The gap between what we say publicly about Mars and what scientists discuss privately has widened into a chasm. This is not a story about conspiracy or cover-up. It is about the natural tension between inspiration and caution, between what we hope is possible and what the data reveals. NASA and other space agencies face an impossible balance: inspire the public and secure funding for exploration, while simultaneously acknowledging dangers so severe they challenge the entire premise of human colonization. How do you encourage a generation of engineers and scientists to reach for Mars while explaining that reaching it might not be enough? That living there, truly living there, presents obstacles that transcend engineering? Tonight, we will journey not across space, but through the hidden architecture of danger that surrounds Mars. We will explore the radiation environment that tears through every living cell, the dust that behaves unlike anything on Earth, the gravity so diminished it may irreversibly alter human biology, and the psychological pressures that no training can fully prepare us for. We will examine the resource crises, the medical impossibilities, and perhaps most unsettling, the unknown unknowns, the dangers we haven't yet discovered because we've never tried to live on another world. This matters now more than ever because the race to Mars has become global, competitive, and accelerated. Nations are investing billions. Companies are building hardware. Launch windows are being calculated. Yet the very urgency that drives these programs may be outpacing our understanding of whether humans can survive there at all, not for a flag-planting visit, but for the years and decades required to call it home. What follows is not meant to extinguish wonder, but to deepen it, to approach Mars with clear eyes and honest questions. Because if humanity is truly to become an interplanetary species, we must first confront the red planet, not as we wish it to be, but as it is. Beautiful, alien, and perhaps more dangerous than we have allowed ourselves to admit. Before we drift deeper into these Martian mysteries, I'd like to ask you something. Wherever you are right now, Whatever moment of day or night has brought you to this video, would you take a moment to comment below? Tell us where in the world you're watching from and what time it is for you. Are you beginning your day or ending it? Are you drifting towards sleep or stealing a moment of wonder between obligations? This journey we're taking together spans the globe, and I'd love to see just how far our community reaches across time zones and continents. Now settle in. Let your thoughts turn toward that red point of light in the sky, and let us examine, carefully and honestly, what waits for us there in the ancient dust and thin cold air of Mars. Mars appears deceptively calm through our telescopes. A rusty world of canyons and dust storms, frozen and silent beneath a thin whisper of atmosphere. But what we cannot see is what makes Mars truly dangerous, invisible, unceasing, and utterly indifferent to human ambition. Radiation bathes the Martian surface every moment of every day. It is not a storm that passes, or a hazard that can be avoided. It is the permanent condition of existence on a world that lost its shield billions of years ago. Earth is wrapped in an invisible fortress. Our magnetic field, generated by the churning molten iron at the planet's core, deflects the solar wind and cosmic radiation that constantly streams through space. It is a planetary force field, stretching thousands of miles into space, bending charged particles away from our atmosphere, protecting the delicate chemistry of life below. Mars once had this protection. Evidence suggests that billions of years ago, Mars possessed a magnetic field of its own, but as the planet's core cooled and solidified, that field collapsed. What remains today is not a shield, but fragments, localized magnetic anomalies scattered across the southern highlands, like the fossils of a protective system long extinct. Without this defense, Mars stands naked before the cosmos. The thin atmosphere that remains, less than 1% the density of Earth's, offers almost no protection. Radiation pours down onto the surface unimpeded, accumulating in the rocks, saturating the dust, turning the entire planet into a radiation environment more hostile than the interior of a nuclear reactor. The assault comes from two directions, each with its own character and lethality. First, there are galactic cosmic rays, particles accelerated to near light speed by distant supernovae and stellar explosions. These particles, primarily protons and atomic nuclei, carry tremendous energy. They slam through matter with such force that shielding becomes extraordinarily difficult. Unlike the radiation we encounter on Earth, which can be blocked by lead or concrete, galactic cosmic rays penetrate deeply, sometimes passing straight through spacecraft walls, through habitats, through human bodies, leaving trails of ionization and cellular damage in their wake. Then there are solar particle events, sudden eruptions from the sun that send waves of high-energy protons surging through the solar system. On Earth, these events trigger auroras, beautiful curtains of light dancing across polar skies, harmless spectacles deflected by our magnetic field. On Mars, they are invisible death sentences. A major solar particle event on Mars would deliver a lethal dose of radiation to anyone caught on the surface without warning. Minutes matter. There would be no time for evacuation, no gradual build-up of symptoms. Radiation sickness would begin within hours. The numbers are sobering, almost incomprehensible when translated into daily experience. A person living on the surface of Mars would receive an annual radiation dose equivalent to receiving more than 50 chest X-rays every single day. Over the course of a year, a Martian settler would accumulate radiation exposure exceeding 200 millisieverts, roughly 40 times the annual limit allowed for radiation workers on Earth. Within 5 years, the cumulative dose would push cancer risk upward by double-digit percentages. Within a decade, cancer would not be a possibility. It would be probable. But the danger is not limited to cancer. Radiation damages DNA with relentless consistency. It breaks chromosomes, triggers mutations, and scrambles the genetic instructions that cells rely upon to function. The body attempts to repair this damage, but repair mechanisms are imperfect. Over time, errors accumulate, tumors form. Cells begin to replicate with corrupted blueprints, each division spreading mistakes deeper into tissues and organs. Perhaps even more disturbing are the cognitive effects. Recent studies of astronauts exposed to elevated radiation levels during deep space missions have revealed troubling patterns. Memory degradation, difficulty concentrating, changes in mood and emotional regulation. The brain, with its dense networks of neurons and delicate electrochemical signaling, is particularly vulnerable to radiation damage. Particles that pass through the brain leave microscopic trails of destruction, severing synaptic connections, killing neurons, disrupting the very architecture of thought itself. A colony on Mars would not just face the risk of cancer. It would face the gradual erosion of mental clarity, the slow unraveling of cognitive function across an entire population. The obvious solution seems straightforward: go underground. If the surface is bathed in radiation, then build beneath it. Excavate tunnels. Construct subterranean habitats shielded by meters of rock and regolith. Some have proposed lava tubes, ancient volcanic tunnels that honeycomb portions of the Martian crust, as ready-made shelters requiring minimal modification. The logic is sound. Rock provides mass, and mass attenuates radiation. A habitat buried beneath 10 meters of Martian soil would reduce radiation exposure significantly, perhaps to levels approaching those experienced by astronauts on the International Space Station. But the challenges of underground construction on Mars are formidable. Excavation requires heavy machinery, power systems, and logistical support far beyond what current mission architectures can deliver. Every ton of equipment sent to Mars costs millions of dollars and months of travel time. Digging into Martian rock, much of it frozen and embedded with subsurface ice, demands drilling technology that can withstand extreme cold and the corrosive, oxidizing chemistry of Martian soil. Then there is the question of structural integrity. Mars experiences seismic activity, Marsquakes that shake the ground with surprising regularity. Tunnels must be reinforced, ceilings must be stabilized. The risk of collapse is not theoretical, it is geological reality. Even if these engineering obstacles are overcome, there remains the psychological cost. Human beings did not evolve to live in caves. Studies of isolated environments, from Antarctic research stations to nuclear submarines, reveal consistent patterns of psychological distress when individuals are confined underground for extended periods. Depression, anxiety, interpersonal conflict. Seasonal affective disorder intensifies in the absence of natural light. The human psyche craves sunlight, open horizons, the experience of sky above and ground below. A colony buried beneath Martian rock might survive radiation, but at what cost to the mental health of its inhabitants? We would trade one invisible killer for another. Then, there is the question that space agencies rarely discuss in public forums, but which looms unavoidably over any long-term settlement scenario: reproduction. If humans are to colonize Mars, they must eventually have children there. Yet we have almost no data on how human reproduction functions in deep space radiation environments. What happens to a developing fetus exposed to galactic cosmic rays and solar particle events? Embryonic cells divide rapidly, their DNA particularly vulnerable to radiation-induced mutations. Animal studies suggest increased rates of miscarriage, birth defects, and developmental abnormalities. On Mars, pregnancy might not just be risky, it might be biologically untenable. Even if pregnancies could be carried to term, what would it mean for a child to grow up in a high-radiation environment? Childhood is a period of rapid growth and cellular division, precisely the conditions under which radiation damage accumulates most aggressively. A generation born on Mars might face cancer rates unheard of on Earth, their lifespans dramatically shortened, their health compromised from birth. This is not speculation. It is the logical extrapolation of known radiobiology applied to Martian conditions. Current shielding technology offers limited solutions. Materials like polyethylene, rich in hydrogen atoms, can absorb some radiation. Water, similarly hydrogen-dense, has been proposed as a dual-purpose resource, serving as both life support and shielding when stored in habitat walls. But these measures reduce exposure. They do not eliminate it. There is no known material light enough to transport to Mars in meaningful quantities that can fully block galactic cosmic rays. Even shielding that reduces radiation by 50% still leaves settlers exposed to doses far exceeding safe limits. Some researchers are exploring more exotic solutions, electromagnetic shields that mimic Earth's magnetic field, pharmaceutical interventions that enhance cellular repair mechanisms, genetic modifications that increase radiation resistance. Each of these approaches remains theoretical, decades away from practical implementation, and each carries uncertainties and ethical complexities that we are only beginning to grapple with. Radiation on Mars is not a problem waiting to be solved. It is a fundamental characteristic of the environment, as intrinsic to the planet as its gravity and its thin atmosphere. To live on Mars is to live in a radiation field. The question is not whether we can eliminate the danger, but whether we can accept it, mitigate it enough to survive, and decide if the cost, measured in health, longevity, and the uncertain fate of future generations, is one we are willing to pay. As we imagine setting foot on the rust-colored plains of Mars, we picture astronauts exploring vast canyons and ancient riverbeds, planting flags in alien soil. But there is something waiting on that surface that does not announce itself with drama or spectacle. It does not roar like radiation or crush like gravity. Instead, it drifts silently on the thin Martian breeze, coating everything it touches with a persistence that borders on malevolence. Martian dust is not merely dirt. It is a chemical weapon forged by 4 billion years of oxidation, a microscopic adversary that may prove more dangerous to human colonies than any threat we can see coming. The first spacecraft to land on Mars sent back images that captivated the world. A barren landscape painted in shades of red and orange, stretched beneath a butterscotch sky. But when those landers began analyzing the soil composition, something unexpected emerged. The Martian regolith, the loose material covering the bedrock, was not chemically inert. It was reactive, aggressive, alive with compounds called perchlorates. These chemicals, which make up roughly 0.5% of Martian soil, are used on Earth as rocket fuel oxidizers and in the manufacture of explosives. On Mars, they exist naturally, scattered across the surface like microscopic landmines, waiting to interact with anything organic. Perchlorates are not just mildly toxic, they are destroyers of life as we know it. When exposed to organic molecules, the building blocks of biology, perchlorates break them apart with ruthless efficiency. This discovery reshaped our understanding of Mars entirely. Scientists had hoped that beneath the surface, protected from radiation. Organic compounds from ancient Martian life might persist. But if perchlorates pervade the soil, they may have spent billions of years systematically erasing any trace of past biology, scrubbing the planet clean of its own history. For human colonists, the implications are immediate and alarming. Any dust that enters a habitat, any particle that contacts skin or finds its way into lungs, carries with it these molecular destroyers. Breathing Martian dust would not simply irritate the respiratory system. It could trigger thyroid dysfunction, disrupt cellular processes, and potentially cause long-term organ damage. The very ground beneath a Martian colony would be chemically hostile to human physiology. But the danger of Martian dust extends far beyond its chemistry. The particles themselves are fundamentally different from the dust we know on Earth. Through millions of years of wind and water erosion, terrestrial dust particles become rounded and smooth. They tumble in rivers, grind against each other in storms, their sharp edges worn away by constant motion. Lunar dust, formed by micrometeorite impacts in the absence of atmosphere, is jagged and glass-like, but at least it behaves predictably. Martian dust occupies an uncanny middle ground. It is extremely fine, much finer than beach sand, with particles measuring just 3 micrometers across, approximately 1/30th the width of a human hair. Under electron microscopes, these particles reveal themselves to be irregular, angular, covered in tiny protrusions and sharp edges that make them cling to surfaces with unusual tenacity. When Apollo astronauts returned from the Moon, they reported that lunar dust had infiltrated every seal, every crevice of their equipment. It smelled, they said, like spent gunpowder. It was abrasive enough to wear through layers of their spacesuits. Some astronauts experienced what they called, quote, zero, a respiratory irritation that cleared up once they returned to Earth. But the Moon has no atmosphere, no global dust storms. Mars does, and Martian dust is lighter, more pervasive, and chemically reactive in ways lunar dust never was. What happened to machinery on Mars gives us deeply troubling clues about what would happen to human lungs. The Mars rovers, our robotic pioneers, have taught us hard lessons about Martian dust. The Opportunity rover, which operated for 14 years before succumbing to a planet-wide dust storm in 2018, provided a slow-motion demonstration of dust's destructive power. Solar panels became coated, reducing power generation with every passing week. Mechanical joints accumulated grit that ground away at precision-engineered surfaces. Instruments designed to last years began failing after months of exposure. The dust was not merely covering equipment, it was infiltrating it, working its way into bearings, seals, electronic housings. And despite engineers' best efforts to design dust-resistant systems, Mars found every vulnerability, every microscopic gap. The dust's behavior becomes even more problematic when we consider Mars's unique atmospheric conditions. With an atmosphere just 1% as dense as Earth's and composed primarily of carbon dioxide, Mars experiences constant static electricity generation. As dust particles tumble across the surface or rise into the atmosphere, they rub against each other and against surfaces, building up electrical charges. Unlike on Earth, where humidity helps dissipate static, Mars' extreme dryness means these charges accumulate and persist. The result is dust that actively clings to surfaces, attracted by electrostatic forces as much as by physical contact. Astronaut suits would become coated within minutes of surface activity. Airlocks, those critical barriers between the hostile exterior and breathable interior, would face an impossible challenge. How do you brush off dust that is electrostatically bonded to fabric and metal? How do you prevent even microscopic quantities from entering the habitat when it behaves more like a magnetic coating than simple dirt? Some researchers have proposed elaborate solutions: multiple-stage airlocks with high-powered air jets, electrostatic cleaning systems, even suits that astronauts would simply leave outside, entering through special ports. But each solution adds complexity, mass, and points of failure to a colony already operating at the edge of technological capability. The history of human engineering suggests that dust finds ways to defeat even the most sophisticated barriers. On Earth, where we have unlimited resources and breathable atmosphere, we still cannot keep dust out of our homes. On Mars, the consequences of failure would not be annoying. They would be catastrophic. The long-term health effects of Martian dust exposure are only beginning to be understood, and what we are learning should give pause to anyone dreaming of Martian cities. Researchers studying simulated Martian regolith have found that its fine particles, when introduced to lung tissue samples, trigger inflammatory responses more severe than terrestrial dust of similar size. The angular particles embed themselves in delicate alveoli, the tiny air sacs where oxygen enters the bloodstream. Unlike Earth dust, which the body's natural defenses can gradually expel, Martian dust's unique properties may make it resistant to the lungs' cleaning mechanisms. Some particles could remain lodged in tissue for years or decades, causing chronic inflammation that leads to scarring, reduced lung capacity, and potentially cancer. Moreover, because Martian dust contains iron oxides in high concentrations, giving the planet its distinctive red color, prolonged exposure could lead to a condition analogous to the lung diseases that plagued miners and industrial workers on Earth. The iron particles may catalyze the formation of reactive oxygen species within lung tissue, molecules that damage cells and DNA. Combined with the perchlorate content and the particles' physical properties, Martian dust represents a three-pronged assault on human health: chemical toxicity, physical abrasion, and catalytic cellular damage. Perhaps most unsettling is how little we truly know. Every sample we have analyzed has come from robotic missions with limited analytical capabilities. We have never observed Martian dust interacting with living human tissue over extended periods. We do not know if there are additional chemical compounds we have not yet detected. We do not know how dust behavior changes in the low-pressure environment of a habitat breach or during the brief exposure of an airlock cycle. We are planning to send humans to a world where the ground itself may be quietly, persistently hostile to their continued survival, and we are doing so with incomplete information. The Martian landscape may appear serene in photographs, a stark desert beauty stretching to distant horizons. But those rust-colored dunes are not merely sand. They are billions of years of oxidation made tangible, a planet's surface transformed into something alien to Earth biology. Every grain contains the chemical memory of a world that lost its magnetosphere, its atmosphere, its water, everything that might have made it hospitable. And now those grains wait, ready to teach arriving humans that Mars does not merely resist colonization through grand visible dangers. It resists through the smallest particles imaginable, through dust that clings and cuts and corrodes, through a microscopic menace that turns the simple act of walking on another world into a potential pathway to slow, cumulative harm. On Mars, you would weigh less than half what you weigh on Earth. At first, this seems like a gift, a lightness of being that might make movement effortless and labor less strenuous. You could jump higher, carry heavier loads, move with an ease you've never experienced. But this apparent advantage conceals one of the most profound, and perhaps insurmountable challenges facing human colonization of Mars. Gravity is not merely the force that keeps our feet on the ground. It is the invisible sculptor of our entire biology, the constant resistance against which every system in our body has evolved to function. Remove that resistance, and the human body does not simply adapt. It begins to unravel. Mars exerts just 38% of Earth's gravitational pull. This means that every step you take, every movement you make, every heartbeat that pumps blood through your body, operates in an environment fundamentally alien to the conditions under which humanity evolved. We are creatures built for 1G, the gravitational constant of Earth. On Mars, we would be living in a state of permanent physiological crisis, fighting against the gradual dissolution of the very structures that keep us alive. The first casualty of reduced gravity is bone. Human bones are not static structures. They are living tissue, constantly breaking down and rebuilding themselves in response to stress. When we walk, run, or simply stand, our bones experience compression and tension. These forces signal to specialized cells called osteoblasts to lay down new bone tissue, maintaining density and strength. But in reduced gravity, this stress diminishes dramatically. The body interprets the lack of pressure as a signal that dense, heavy bones are no longer necessary. It begins to dismantle them. Astronauts on the International Space Station, living in complete microgravity, lose between 1 and 2% of their bone mass every month, primarily in the hips, spine, and legs. Even with rigorous daily exercise regimens, 2 hours of resistance training and cardiovascular work, they cannot fully prevent this loss. The treadmills and resistance machines can simulate some gravitational stress, but not the constant, persistent load of simply existing under Earth's gravity. Now consider Mars, where gravity is not absent but merely reduced. Will colonists lose bone at the same rate as astronauts in orbit? At half that rate? A quarter? The truth is, we don't know. No human has ever lived in partial gravity for an extended period. Mars would be our first experiment, and the colonists themselves would be the test subjects. The implications stretch across years. After 6 months on Mars, a colonist might lose 3 to 12% of their bone density. After a year, 6 to 24%. These numbers represent not just statistics, but physical reality, the gradual brittleness of the skeleton, the increasing fragility of the frame that supports everything we are. Hip fractures, spinal compression, bones that snap under stress that would barely register on Earth. And unlike muscle, which can be rebuilt relatively quickly, bone recovery is slow, measured in months and years of gravitational loading. Muscle follows a similar trajectory of decline. On Earth, our muscles work constantly against gravity, maintaining posture, stabilizing joints, circulating blood. In reduced gravity, this work diminishes. The body, ever efficient, begins to dismantle what it no longer needs. Muscle mass decreases, strength fades. The cardiovascular system, no longer required to pump blood upward against Earth's full gravitational force, begins to decondition. The heart itself may shrink, becoming less efficient, less capable of handling the demands of full gravity should a return to Earth ever be necessary. This leads to perhaps the most sobering question facing any Mars colonization effort. The point of no return. How long can a human live on Mars before returning to Earth becomes physiologically impossible? Current data from the ISS suggests that astronauts who spend 6 months in microgravity require months of rehabilitation before they can walk normally again. Some experience orthostatic intolerance, a condition where standing upright causes dizziness and fainting because the cardiovascular system can no longer efficiently pump blood against gravity. These astronauts spent half a year in zero gravity. What happens to someone who spends 5 years at 38% gravity? 10 years. An entire lifetime. There may come a moment, measured not in dramatic revelation, but in the slow accumulation of physiological change, when a Mars colonist can no longer survive the crushing weight of Earth. Their bones would be too fragile, their muscles too weak, their heart too small to handle the demands of full gravity. At that point, they would become permanent residents of Mars, not by choice, but by biology. They would be the first humans for whom Earth is not home, but an alien world as hostile to their adapted physiology as Mars once was to their ancestors. And what of children? The question of pregnancy and development in reduced gravity remains one of the greatest unknowns in space medicine. On Earth, gravity plays a crucial role in fetal development. Fluid distribution, organ positioning, bone formation all occur under the constant downward pull that has shaped mammalian reproduction for millions of years. Would a fetus develop normally at 38% gravity? Would the skeletal system form properly without the full compressive forces of Earth? Would the cardiovascular system develop the strength necessary for life in higher gravity? Or would it calibrate itself to Mars, creating children who could never visit the world their parents came from? No mammals have ever been conceived, gestated, and born in reduced gravity. The experiments that would answer these questions have never been conducted, not for ethical reasons primarily, but because no platform exists to house them. We have theoretical models, speculation, informed guesses based on partial data from pregnant animals on short-duration spaceflights. But models are not certainties. The first child born on Mars would be a pioneer in the most profound sense, a test of whether human reproduction can transcend the gravitational conditions under which it evolved. Beyond bones and muscles lies another concern: fluid redistribution. On Earth, gravity pulls blood and other fluids downward, pooling them in the legs and lower body. The cardiovascular system has evolved elaborate mechanisms to counteract this, maintaining appropriate pressure in the brain and organs. In reduced gravity, fluids shift upward. Blood pressure in the head increases. The eyes experience swelling. Some astronauts develop vision problems, a condition called spaceflight-associated neuroocular syndrome, where the optic nerve swells and the eyeball flattens due to increased intracranial pressure. These changes can be permanent, a price paid for time spent beyond Earth's gravitational embrace. On Mars, would this fluid shift be less severe than in microgravity? Almost certainly. But less severe is not absent. Colonists might experience chronic headaches, vision changes, cognitive effects from sustained elevated brain pressure, all subtle degradations that compound over time. The most elegant solution to the gravity problem would be artificial gravity, rotating habitats or centrifuges that simulate Earth normal conditions through spin. Centrifuge designs have been proposed for decades, cylindrical habitats rotating at precise speeds to generate 1G along their inner surfaces. In theory, colonists could sleep in these rotating sections, allowing their bodies 8 hours of gravitational therapy each night. But constructing such systems on Mars presents extraordinary engineering challenges. The structures must be massive to avoid problems with Coriolis forces, the disorienting effects of rotation. They must be perfectly balanced, constantly monitored, maintained with precision in an environment where spare parts and expertise are desperately limited. And even if built successfully, would 8 hours of artificial gravity per day be enough to counteract 16 hours at 38%? We don't know. The gravity dilemma forces us to confront an uncomfortable truth. We are not merely creatures of Earth by circumstance. We are creatures of Earth by design, shaped across millions of years to function in one specific gravitational environment. Mars does not simply lack breathable air and surface water. It lacks the fundamental physical conditions under which our biology operates. Living there would not be adaptation, it would be transformation, a slow metamorphosis into something no longer quite human in the way we currently understand the term. Whether that transformation is survivable, sustainable, or even reversible remains one of the deepest mysteries facing the future of human space exploration. On Mars, we would not simply be colonists. We would be evolutionary pioneers, testing the limits of how far human biology can bend before it breaks. Distance is not only measured in miles, sometimes it is measured in silence. On Mars, when a colonist sends a message to Earth, the reply does not arrive immediately. There is no real-time conversation, no spontaneous laughter shared across a video call, no comforting voice responding the moment fear or loneliness takes hold. Instead, there is a delay. 22 minutes on average for a signal to travel from Mars to Earth and back again. In practical terms, this means every exchange becomes asynchronous, a form of communication closer to letters sent across an ocean than a phone call between friends. The psychological weight of this delay cannot be overstated. Human connection thrives on immediacy, on the rhythm of back and forth dialogue, on the subtle cues of tone and timing that tell us we are heard, that we matter, that we are not alone. On Mars, that rhythm breaks. A colonist experiencing a medical emergency, a moment of panic, or simply the crushing weight of homesickness, must wait nearly half an hour for reassurance. By the time the reply arrives, the moment has passed. The crisis has either resolved or worsened. The need for connection has either been suppressed or transformed into something darker. This is not speculation. It is a known variable, one that transforms Mars from a physical challenge into an emotional abyss. Every conversation becomes a monologue. Every question hangs in the silence of space, unanswered until the laws of physics permit a response. In that silence, the mind begins to wander. It begins to doubt. It begins to measure the true distance between worlds, not in kilometers, but in moments of isolation that accumulate like grains of Martian dust. On Earth, we have tested the limits of human endurance in isolation. Antarctica, perhaps the closest analogue we have to Mars, offers sobering lessons. Research stations buried beneath ice and darkness have documented what happens when humans are cut off from the world for months at a time. The phenomenon known as winter over syndrome manifests in subtle ways at first: irritability, difficulty concentrating, emotional numbness. Then it deepens. Sleep cycles deteriorate. Social bonds fray. Some individuals withdraw entirely, spending days in their quarters, staring at walls, unable or unwilling to engage with their companions. These are not weak individuals. They are scientists, researchers, people selected specifically for their psychological resilience. Yet Antarctica breaks them in small ways. And Antarctica, harsh as it is, still offers something Mars cannot: the knowledge that rescue is possible, that home is reachable, that the isolation has a definite end date. Mars offers no such comfort. Once on the surface, colonists are committed for years, possibly for life. The return journey, if it exists at all, is measured not in weeks, but in alignment windows between planets, in launch trajectories that occur only once every 2 years. The habitats themselves compound this psychological burden. Popular imagination envisions sprawling Martian cities, domed biodomes filled with gardens and open spaces. The reality will be far more claustrophobic. Mass constraints for rocket launches mean every kilogram counts. Early Mars habitats will be small, cramped, utilitarian. Think less orbital paradise and more submarine interior. Modules connected by narrow tunnels, low ceilings, recycled air that always carries a faint metallic taste, no windows or only small reinforced viewports, because radiation shielding requires thick walls. Studies of confined environments on Earth, submarines, space stations, isolated research outposts reveal consistent patterns. After weeks or months, the same walls begin to feel oppressive. Personal space becomes precious, fiercely guarded. Minor annoyances, a crewmate's laugh, the way someone chews food, small habits that would be insignificant on Earth, transform into sources of intense irritation. Interpersonal conflict is not a possibility in small isolated groups under extreme stress. It is an inevitability. NASA understands this. Crew selection for long-duration missions involves extensive psychological screening, personality compatibility assessments, conflict resolution training. Yet no amount of preparation can fully eliminate the friction that emerges when humans are forced into proximity with no escape, no privacy, no relief. On Earth, when relationships become strained, we leave. We take a walk. We visit a friend in another city. We create distance. On Mars, there is nowhere to go. The habitat is the entire accessible world. Beyond its walls lies only death. Then there is the sky, or rather, what the sky reveals. Astronauts in orbit around Earth often describe the quote 3, a profound cognitive shift that occurs when viewing Earth from space. The planet appears as a unified whole, borderless and beautiful, floating in the void. It inspires awe, connection, a sense of belonging to something greater. On Mars, colonists will experience something different, something reversed. They will stand on the Martian surface and look up at the rust-coloured sky. And there, among the stars, they will see Earth. Not as a majestic sphere filling their view, but as a pale blue dot, barely distinguishable from other points of light. Carl Sagan spoke of Earth as a modern quote 4, when Voyager photographed it from the edge of the solar system. For Martian colonists, this will not be a philosophical concept. It will be their daily reality. Everything they have ever known, every person they have ever loved, every memory of warmth and rain and birdsong, reduced to a single pixel of light in an alien sky. The psychological term for this is quote 5, though. That phrase feels inadequate. It is not mere homesickness. It is the acute awareness of everything that has been lost, everything that can never be recovered. No Martian colonist will feel grass beneath their feet again. None will breathe unfiltered air. None will hear the ocean or feel natural rain. These experiences, taken for granted on Earth, become impossibilities, ghosts of a life that belongs to another world. Sunlight on Mars is different too, weaker, filtered through a thin atmosphere laden with dust. The planet receives only 44% of the sunlight that Earth does. For humans evolved under Earth's bright sun, this perpetual dimness has consequences. Seasonal affective disorder, the depression linked to reduced sunlight exposure during winter months, is well documented on Earth. On Mars, it would be chronic, unending. Every day would be a winter day. Every sunrise would cast long shadows through perpetual twilight. Artificial lighting can help, but it cannot fully replicate the spectrum and intensity of natural sunlight. Colonists would live under LED panels, their circadian rhythms constantly fighting against an environment that feels fundamentally wrong. Sleep disorders would become endemic. Vitamin D deficiencies would require constant supplementation. The simple act of waking up, of facing another dim Martian day in a cramped habitat, would require a psychological fortitude that few possess indefinitely. Perhaps the darkest consideration is one that NASA rarely discusses publicly, though it exists in contingency planning documents buried deep in mission archives: the suicide contingency. What happens when a crew member, overwhelmed by isolation, confinement, and the impossibility of escape, decides they cannot continue? On Earth, mental health crises can be managed with intervention, hospitalization, medication, therapy. On Mars, options are limited. There are no psychiatric hospitals, no trained counselors beyond whatever rudimentary support the crew can provide each other. If someone becomes a danger to themselves or others, there is no authority to call, no institution to provide care. Some mission planners have quietly considered protocols for restraint, sedation, isolation of unstable crew members. Others acknowledge that in the worst case, a mission might simply lose a colonist to despair. This is not discussed in press conferences or recruitment materials. It is too dark, too real, too at odds with the heroic narrative of Mars colonization. But it is a possibility that cannot be ignored. Human psychology has limits. Mars will test those limits every single day. The journey to Mars is not measured only in months of travel. It is measured in accumulated moments of silence, in delayed conversations, in walls that close in sunlight that never feels quite right, in a blue dot in the sky that represents everything unreachable. To send humans to Mars is to ask them to endure a psychological gauntlet unlike anything our species has faced. And the question we must honestly confront is not whether some individuals could survive it. The question is whether enough could endure it long enough to build something lasting, or whether Mars will remain forever a place that breaks the human spirit before it can take root. Beneath the rusty surface of Mars lies water, frozen and waiting. For decades, this discovery has fueled our dreams of Martian colonies. Yet the promise of water on Mars is not the same as the reality of drinking it, growing food with it, or sustaining life through it. As we examine the resource challenges facing future colonists, we begin to understand that Mars does not simply lack resources. It locks them away behind barriers of chemistry, energy, and time. Every drop of water, every breath of oxygen becomes not a given, but a victory earned through constant technological struggle. This is the paradox of Martian survival. Surrounded by the ingredients for life, yet perpetually on the edge of scarcity. Water exists on Mars in abundance, frozen in polar ice caps that gleam white against the red landscape, trapped in subsurface deposits that radar has revealed stretching across vast regions. Early mission planners celebrated these discoveries as confirmation that Mars could support human settlement. But ice on Mars is not simply frozen water waiting to be melted. It is contaminated with perchlorates, toxic compounds that permeate the Martian regolith. These chemicals, used on Earth as rocket fuel and explosives, are abundant in Martian soil at concentrations that would be lethal to humans. Even after extraction and melting, the water must be extensively purified, requiring energy-intensive filtration systems that must operate flawlessly, perpetually, without failure. The energy requirements for water extraction reveal a challenge that mission planners are only beginning to fully comprehend. To mine ice from beneath the surface requires drilling equipment, heating systems to melt the frozen deposits, pumping mechanisms to transport the water, and purification systems to remove the perchlorate. Each step demands power. Current projections suggest that a colony of just 100 people would require several megawatts of continuous power simply to maintain water supplies. On Earth, this would be a modest demand. On Mars, where solar panels produce only 40% of their Earth-equivalent output due to distance from the sun and dust accumulation, and where nuclear reactors must be transported across interplanetary space, energy becomes the ultimate limiting factor. Every litre of water extracted represents kilowatt-hours that cannot be used for heating, life support, or food production. Oxygen presents its own labyrinth of challenges. NASA's MOXIE experiment, carried aboard the Perseverance rover, has demonstrated that oxygen can be extracted from Mars's carbon dioxide atmosphere through a process called solid oxide electrolysis. The technology works. In controlled tests, MOXIE has successfully produced oxygen at rates that could, theoretically, be scaled up to support human breathing. But the gap between a successful experiment and a life-sustaining system is measured not in iterations, but in orders of magnitude. MOXIE produces oxygen in amounts measured in grams per hour. A single human requires approximately 800 grams of oxygen per day. A colony of 100 would need 80 kilograms daily, requiring systems far larger, far more complex, and far more power-hungry than anything yet demonstrated. And these systems cannot simply work most of the time. They must work all of the time, in conditions of extreme temperature variation, with components exposed to abrasive dust and corrosive perchlorates. The concept of closed-loop life support sounds elegant in theory. A perfectly balanced system where nothing is wasted, where every exhaled breath is captured and recycled, where water from human waste is purified and returned to drinking supplies, where oxygen and carbon dioxide dance in perfect equilibrium. The International Space Station has made remarkable progress toward this ideal, recycling approximately 90% of water and generating much of its oxygen from that recycled water. But the ISS orbits Earth, only hours away from resupply missions. When components fail, and they do fail with regularity, replacement parts arrive on the next cargo vehicle. On Mars, there is no next cargo vehicle, not for 26 months. And during those months, entropy works against perfection. Seals degrade, filters clog, pumps wear out, sensors drift out of calibration. Every mechanical system ever built by humans eventually breaks. The question is not whether, but when, and what happens in the hours between failure and repair. Food production on Martian soil is not simply impossible, it is dangerous. The perchlorates that contaminate the water also saturate the regolith. Plants grown in Martian soil, even inside pressurized greenhouses, would absorb these toxins. Studies with earth plants exposed to perchlorate-laden soil show accumulation in edible tissues at levels that would damage human thyroid function and disrupt metabolism. This means all food production must rely on hydroponics or aeroponics, systems where plants grow in nutrient-rich water or mist, isolated from Martian soil entirely. Yet hydroponic systems are energy-intensive, requiring artificial lighting that mimics the sun's spectrum, heating to maintain growth temperatures, and pumps to circulate nutrients continuously. A colony cannot simply plant seeds and wait for harvest. It must operate what amounts to an industrial farm, indoors, under artificial conditions, with no room for crop failure. If a fungal infection spreads through the hydroponic systems, if a power failure causes temperatures to plummet, if nutrient imbalances stunt growth, the colony faces not mere inconvenience but potential starvation, months before any relief could arrive from Earth. The fragility of Martian life support reveals itself most starkly when we consider cascade failures. Systems are interconnected. A failure in power generation reduces water extraction capability. Reduced water extraction means less oxygen production through electrolysis. Less oxygen forces the colony to draw down reserves. As reserves deplete, stress increases on backup systems, which were never designed for continuous operation. Backup systems fail faster than primary systems because they lack the same level of redundancy and maintenance. When backups fail, survival windows collapse from days to hours. Humans can survive weeks without food, days without water, but only minutes without oxygen. A single critical failure in oxygen generation, if it cannot be repaired within hours, transforms a Mars colony from humanity's greatest achievement into its most remote tomb. Perhaps most sobering is the resupply problem. Launch windows from Earth to Mars open only once every 26 months when the planets align favorably. Between these windows, Mars colonies are entirely on their own. If a crucial component fails, if food production falls short, if medical supplies run low, there is no emergency shipment, no rapid response. The cavalry is 2 years away, travelling at tens of thousands of miles per hour across tens of millions of miles of void. Current mission architectures assume that pre-positioned supplies and robust redundancy will bridge these gaps. But assumptions are not survival. Every space program in history has experienced surprises, failures that emerged from unexpected interactions between systems, from conditions that simulations did not predict. On Mars, surprises do not lead to mission adjustments. They lead to critical decisions about who receives remaining oxygen, which systems to power down, how to extend survival by days or weeks while knowing that rescue is still months or years away. Some researchers propose that early colonies should vastly oversize their resource production capabilities, building redundancy through abundance rather than efficiency. If water extraction can support 1,000 people, then a 100-person colony has a 10-fold safety margin. If oxygen production can supply 10 times the required amount, then partial failures become survivable. But oversizing multiplies costs, energy demands, and the sheer mass that must be transported from Earth. Every kilogram launched to Mars costs thousands of dollars. Redundancy, however prudent, may price colonies beyond feasibility. The water and oxygen crisis on Mars is not a problem waiting to be solved. It is a condition to be endured. Future colonists will not live on Mars. They will live inside elaborate machines, entirely dependent on the continuous functioning of technology, in an environment that corrodes, abrades, and starves those very systems. The Red Planet offers no grace period, no forgiveness for oversight. It is a world where resources exist tantalizingly close, yet separated from human need by barriers of energy, chemistry, and distance. To establish a colony on Mars is to accept that every breath, every drink, every meal will be a calculated victory over an environment fundamentally indifferent to human survival. This is not the romantic frontier of pioneers clearing land and planting crops. This is survival through industrial process, where the difference between life and death is measured in kilowatts, filter efficiencies, and the hope that nothing critical breaks before replacement parts can arrive from a world millions of miles away. On Earth, medicine is built on an assumption so deep we barely notice it. Help is always nearby, a surgeon on call, a specialist across town, a helicopter, an ICU, a pharmacy stocked with everything from antibiotics to antivenom. Even in remote places, the invisible net of global healthcare stretches overhead, ready to catch us when something goes wrong. On Mars, that net is gone. Here, distance is not just miles. It is finality. There is no evacuation, no emergency flight back to Earth. No, we'll transfer you to a better hospital. Whatever happens on Mars stays on Mars, including every medical problem no one planned for. Imagine a colony barely a few dozen people strong. The air outside is lethal. The gravity is 1/3 of what your body evolved for. Cosmic radiation seeps silently through walls and bone. In this fragile outpost, medicine is not a system. It is a room, a cabinet, and one overworked human with a limited set of tools. Now imagine the first emergency. A crew member slips in a dust-coated airlock, falls, and doesn't get up. Internal bleeding. Possible head trauma. On Earth, lights would flare in a modern trauma bay. Teams would converge. Machines would hum to life. On Mars, there is only the med bay, about the size of a small bedroom, with a portable ultrasound, a basic ventilator, and a single surgeon who might also be the colony's anaesthetist, internist, and dentist, because there is no one else. Emergency surgery in low gravity is not just hard. It borders on science fiction. In orbit, fluids don't pool, they float. On Mars, gravity is stronger than on the ISS, but still alien. Blood won't behave quite like it does on Earth. It may not drain as expected. It may aerosolize more easily, spreading microscopic droplets through a sealed habitat where air is recirculated for months. Operating rooms on Earth are designed to be pristine, controlled worlds. On Mars, every room is a compromise. Dust creeps in through every seal. Power flickers. Equipment fails and can't be replaced for years. In an emergency laparotomy to stop internal bleeding, the surgeon must balance not just the patient's blood pressure, but the colony's entire infrastructure, oxygen reserves, power availability, even whether they can spare the personnel to assist. And hovering over every incision is a terrifying reality. If something goes wrong, there is no higher level of care, no medevac, no second opinion that arrives in person. The colony is the first line of defense, and the last. Even if the surgery goes perfectly, medicine runs on more than scalpels and courage. It runs on chemistry. On Earth, medications flow constantly, manufactured in one place, flown to another, refrigerated, rotated, discarded when they expire. Pharmacies don't need to stock 10 years of chemotherapy in a single room. They rely on a planet-wide supply chain that never truly stops. On Mars, every pill, every vial, every dose has to fit in the mass budget of a rocket and survive years of transit, storage, and radiation. Most medications have limited shelf lives. Insulin, for example, is measured in months. Many biologics require cold chains we struggle to maintain even in wealthy cities. Cosmic radiation doesn't just damage human DNA, it degrades chemical bonds. Over years, medications can lose potency or transform into something unknown. Labels will still read antibiotic, but no one can say with certainty what actually lies inside after 5 years on a planet bathed in radiation. Manufacturing complex pharmaceuticals on Mars is not as simple as we'll bring a small factory. Modern drug production is a ballet of precise temperatures, sterile environments, specialized reagents, and highly regulated processes. To replicate that on a young colony would mean building an entire parallel civilization. Chemical plants, quality control labs, sterile packaging lines, all for a population that might fit on a single city bus. The result is a quiet, looming dilemma. Colonists will eventually face serious illnesses with a pharmacy that ages faster than they do. Some of those illnesses sound mundane on Earth, trivial even. A cracked tooth, a cavity that hits the nerve, a wisdom tooth impacted in someone who was 18 at launch and 24 after the first Martian synod. On Earth, dental emergencies hurt, but rarely kill. On Mars, a raging dental infection in an era of depleted antibiotics can mean sepsis in a habitat where you can't open a window or add new staff. Toothaches aren't just annoyances, they are threats to the entire mission. Consider appendicitis. On Earth, it is so routine that hospitals treat it as standard practice. But on Mars, an inflamed appendix can become a countdown. If your colony's only surgeon is out on an EVA, or sick, or injured, the options narrow quickly. There is no send them to the nearest hospital. The nearest hospital is a blue dot in the sky, 140 million miles away. This is where once simple ailments begin to look like death sentences in disguise. Beyond these acute crises, another kind of threat is quietly incubating in every colonist's cells. Radiation. The same charged particles that chip away at electronics also strike DNA. They create breaks, mutations, subtle changes so small they are invisible for years, until they aren't. Cancers that would have emerged at 70 on Earth might appear at 40 on Mars, or earlier, or more aggressively. No one truly knows. Treating cancer on Earth already tests our most advanced cities. It requires imaging scanners, specialized drugs, radiation therapy machines the size of buses, and teams of oncologists, physicists, and nurses. On Mars, there may be a single CT scanner, or none. There might be one oncologist on a good day, or a general physician reading a handbook on tumors between routine health checks. Radiation-induced cancers are not an if. They are a when and how often. And they will arrive in a place with minimal ability to respond. Layered on top of all this is a more subtle danger, the numbers themselves. A small population is fragile, medically and genetically. On Earth, we benefit from billions of people. Someone somewhere has the rare blood type. Someone else has the obscure specialization. Our genetic diversity acts as a buffer against inherited diseases and immune vulnerabilities. On Mars, a colony might start with a few dozen hand-picked individuals, then a few dozen more, years later. For a long time, the colony is not a city. It is an extended, isolated family. In such small populations, genetic bottlenecks loom in the future. Certain hereditary conditions might become more common purely by chance. Some immune system quirks might cluster in ways we can't yet predict. Over generations, this could shape what diseases are common on Mars in ways entirely different from Earth. The same scarcity applies to knowledge. You can't bring every kind of doctor. You might bring one excellent surgeon, one internal medicine specialist, one psychiatrist. But what happens if the psychiatrist leaves or dies or simply burns out? What if the one pediatrician is needed before any children are actually born? Expertise doesn't just have to be present, it has to last. Some will argue that telemedicine solves this. Earth doctors, advising in real time from across the void. In principle, it's beautiful. In practice, Mars has a built-in lag that no technology can erase. At closest approach, messages between Earth and Mars still take several minutes each way. At worst, they take up to 22 minutes, sometimes more, per direction. A video call becomes a series of recorded messages. A conversation about chest pain turns into describe symptoms, wait nearly an hour for guidance, adjust, repeat. For routine check-ins, telemedicine might work. Adjust this medication. Try this physical therapy exercise. But for a crashing patient whose blood pressure is collapsing right now, a 40-minute round-trip delay is the difference between life and death. The doctor on Earth becomes a ghost consultant, always late, always watching the past, never the present. Which leads to another emerging character in this story, medical AI. If there is no time for human experts to intervene, perhaps machines can. An AI surgeon assistant, an AI diagnostician trained on millions of cases, an AI that can review vital signs, scan an ultrasound, and whisper, "Make the incision here." Such systems might be essential for any long-term colony. AI doesn't fatigue. It doesn't leave. It can hold the sum of global medical literature in its memory. In a crisis, a Martian physician could lean heavily on algorithms that flag subtle patterns and suggest next steps. But AI also faces gravity of a different kind, reality. On Mars, data will be limited. The number of patients tiny. Many conditions will present differently in 38% gravity under chronic radiation, with altered immune systems and microbiomes shaped by closed habitats and recycled air. AI trained entirely on Earth-based medicine may misinterpret signals in this alien context. It may not recognize how bones remodel in low gravity, how wound healing changes, how new, Martian-specific syndromes arise. And when it gets something wrong, there is no appeals court, no second hospital to try. The AI's recommendation becomes the colony's best and only guess. So healthcare on Mars becomes a paradoxical landscape, at once impossibly thin and crushingly heavy. Thin in resources, staff, and equipment. Heavy in consequence, responsibility, and uncertainty. NASA and other space agencies know this. Quietly, in technical reports and risk matrices, they list inadequate medical care as a mission-threatening hazard. They run simulations in underwater habitats and polar stations. They test portable surgical kits in parabolic flights. They study medication degradation in orbit, trying to map out how far the body and our technology can be stretched. But even the most advanced planning cannot change one basic fact. On Earth, medicine is woven into civilization. On Mars, medicine must be woven into survival. In such a place, every crew member's body becomes unexplored terrain. Every minor ache, every unexpected bruise, every odd lab result is not just a symptom. It is a question, asked in a language we are still learning to read, in an environment we were never meant to inhabit. For a species that has filled a planet with hospitals and clinics, the idea that illness could once again become a fundamental, unsolvable threat feels archaic, almost medieval. Yet on Mars, despite all our technology, that is the frontier we step back toward. Not because we are unprepared, but because some forms of preparation require more than equipment. They require time, experience, and generations of trial and error. Things that, on a world 140 million miles away, we simply do not yet have. We imagine Mars as a solved picture. Red dunes, a thin sky, frozen poles, dust storms rolling across empty plains. But in truth, we are staring at it the way ancient sailors stared at the edge of their maps, where the land faded into blank parchment, and the words, "Here be dragons," took the place of knowledge. For all the satellites, rovers and landers, Mars is still mostly unexplored. We have walked only with cameras and wheels, never with feet and lungs and fragile human bodies. And that means some of the most important dangers may be the ones we haven't even thought to name yet. Imagine, beneath the rusty stones and frostbitten soil, something small. Not a ruin, not a fossil, but a microbe. A Martian organism, if it exists at all, would not look like the life we know. It might live in briny streaks under the surface, or locked in pockets of ice, awakening only when conditions briefly allow it. To our instruments, it could be almost invisible, just a chemical whisper in the regolith. If humans arrive and begin to dig, melt, drill, and vent warm air into sealed habitats, we change Mars. We add liquid water, heat, pressure. We create islands where a hidden biosphere, dormant for millions of years, might suddenly find opportunity. The contamination problem doesn't just run one way. It is not just about Earth microbes threatening Mars. It is also about Mars, in the quiet persistence of its own life, threatening us. Our bodies, our crops, our microorganisms are tuned to Earth's biology. A Martian microbe might be harmless. It might be chemically incompatible, unable to use our cells as fuel. Or, through pathways we don't yet understand, it might interact with our immune systems in ways we have never seen, triggering chronic inflammation, strange allergies, or subtle long-term effects that only become clear after months or years of exposure. Even a microbe that can't infect us directly might clog filters, colonize water systems, or corrode critical equipment, thriving in the artificial oases we create. Similarly, our own life forms, carefully sterilized yet never completely clean, could leak into Martian soil. Earth bacteria on suit joints, habitat vents, or discarded waste might adapt in unexpected ways under low gravity, intense radiation, and strange chemistry. Over time, those invaders could blur the line between what is native and what is imported, making it harder to study Mars itself and harder to control the ecosystems we unintentionally build. Mars, as it is a harsh chemistry experiment waiting to be disturbed. Its soil contains perchlorates, salts that can disrupt human hormones and damage organs. But that is just one known ingredient in a planetary cocktail we haven't fully sampled. We have brought only small sets of materials to Mars so far: aluminum, titanium, glass, a handful of plastics. A crewed mission brings something completely different: tons of structural metals, complex polymers, electronics, textiles, lubricants, adhesives, insulation, and biological waste. On Earth, we test materials in simulated Mars chambers, under cold, thin carbon dioxide, with artificial dust. But the real planet is not a lab. Ultraviolet light slices down almost unfiltered. Temperature swings fracture materials with daily violence. Charged particles thread through circuits and coatings. Over time, the Martian environment might trigger chemical reactions we haven't anticipated. A plastic believed to be stable could become brittle when saturated with fine dust and bathed in UV, cracking seals or airlocks years earlier than expected. Exotic alloys could react with perchlorate-laced dust in rare combinations, corroding slowly from the inside out. Lubricants might evaporate or polymerize in low pressure, turning smooth mechanisms into grinding traps. Even the interaction between human sweat, cleaning fluids, and Martian dust could create residues that foul filters and poison closed-loop systems. Many of these problems would not show themselves in the first week or even the first year. They would emerge slowly, a series of small, unexplained failures that accumulate like hairline cracks in an old ship's hull. Above the surface, another unknown waits in the sky. Mars has an atmosphere, but it is thin, less a protective blanket and more a whisper of air. On Earth, countless meteoroids burn up harmlessly in that thick layer. On Mars, many of them do not. They survive, reaching the ground with more of their mass and more of their energy intact. For a settlement, that changes the odds. A tiny rock that would flash out as a streak of light in our skies might arrive on Mars as a solid projectile, slamming into the surface with enough force to punch through thin roofs, expose buried cables, or rupture pressurized tanks. A small crater on an empty plain is a scientific curiosity. The same impact within a few hundred meters of a habitat could be a cascading disaster. Dust clogging life support intakes, shock waves fracturing windows, debris piercing suits or vehicles. Over years and decades, the statistics matter. Even if large impacts are rare, the number of small ones shifts from abstract meteorites to concrete risk. It is one thing to see a meteor shower through Earth's safe, warm sky. It is another to hear the faint beep of an alarm in a Martian habitat and wonder if this is the day a random stone from deep space found your fragile outpost. And then there is the ground beneath your feet. Mars is not geologically dead. We have recorded Marsquakes, vibrations rumbling through the crust, subtle but real. Yet we have only scraped at the surface of what this means for long-term settlement. Most of our detailed seismic measurements come from a single lander in a single location. The rest of the planet remains largely unmapped in terms of how it moves, shifts, and flexes. A habitat built on seemingly solid bedrock could find itself above a fracture zone that creaks to life decades later. A buried lava tube used as a shelter might experience slow, unseen erosion, until one day a section collapses under stored equipment or a greenhouse. A region that appears quiet could be connected to distant stresses, transmitting distant Marsquakes as trembling that loosens bolts, misaligns machinery, or weakens support structures. On Earth, we have centuries of experience with earthquakes and building codes. On Mars, the first settlers would be writing that book in real time, with their own lives as the footnotes. Individually, each of these unknowns, a lurking microbe, an odd chemical reaction, a stray meteor, a hidden fault line, might be manageable. But the real danger may not be in any one factor. It may be in the way small stressors stack and interact. A slightly degraded air filter from dust, combined with a minor radiation-induced glitch in a sensor, plus an unexpected chemical deposit in a water line, none catastrophic alone, might together lead to a misreading of tank levels, a delayed response, or a wrong decision in a moment that requires perfect clarity. A colony may not fail because of one massive event, but because tiny problems accumulate faster than they can be understood and repaired, especially when every spare part is months away by rocket. This is the cumulative effect problem. The idea that on a hostile world, it is not always the obvious dragons that get you, but the swarm of gnats you never noticed until they block out the sun. History offers quiet warnings. Early polar explorers expected cold, they expected hunger, but many did not expect scurvy to twist their bodies from within, or ice to shear their ships apart like glass, or unseen currents to carry them off course. Sailors in the age of discovery knew little of tropical diseases that would empty ships in weeks. Climbers on Everest planned for thin air and ice, but not always for jet stream winds that shred tents or microscopic frost that erodes ropes. Time and again, humans have stepped into new environments confident in their calculations, only to discover that nature writes its own rules in fine print. Mars will be no different. Some of its rules we already know: radiation, dust, gravity, isolation. Others we suspect but cannot yet map. And then there are the ones we don't even know how to ask about. How will human sleep change after years under a pink sky? What unknown chemical cycles emerge in a closed habitat filled with Martian dust and recycled air? How will our bodies age in a place where every breath, every sip, every step is mediated by machines? Those answers will not arrive fully formed from orbit. They will emerge only when people are there, breathing recycled oxygen, walking out into the cold, making mistakes, and learning. The first Martian settlers will not just be colonists, they will be test subjects, living inside an experiment with no true control group. Mars invites us not just to dream, but to confront the limits of what we know. Behind every rover photo and every mission plan lies a shadow of uncertainty. Not a reason to turn away, but a reason to step carefully, to recognize that the most serious risks might be the ones we haven't yet imagined. Beyond the maps and simulations, beyond the confident diagrams and optimistic timelines, Mars remains, in some deep sense, a question. And humans, fragile and curious, would be the ones sent to find its answer. If you listen to the public announcements, Mars is a horizon, a destiny, an inevitable next step. Artist renderings show glowing domes beneath pale salmon skies, astronauts planting flags, children drawing new constellations through pressurized windows. The journey is framed as difficult, but possible, risky, but manageable, a natural continuation of Apollo. Behind that story lives another one. Inside meeting rooms with no cameras and teleconferences with no press, the language shifts. PowerPoints lose the inspirational taglines and gain phrases like catastrophic loss of crew, unquantified hazard, and not yet technically feasible. The dream of Mars is still there, but on internal documents, it is surrounded by a halo of warnings. Every space agency carries two narratives at once, one for the public imagination, one for the engineering reality. In the case of Mars, the distance between those two has never been larger. Over the last few decades, pieces of that hidden narrative have slipped into the open. Radiation risk assessments, once labeled for official use only, have been summarized in conference papers. Long-duration mission simulations like Mars 500 and NASA's HIC's analogues in Hawaii have quietly documented psychological breakdowns, interpersonal conflicts, and stress overloads that rarely make it into glossy highlight reels. Advisory panels have published reports that read less like invitations to a grand adventure and more like cautionary notes taped to the door of an unexplored cave. In these declassified studies, astronauts are not heroic silhouettes on a poster. They are biological systems placed into an environment that does not want them. One Mars mission scenario estimates cumulative radiation doses exceeding current lifetime limits for astronauts before they even set foot on the planet. Another warns that unknown synergies between low gravity, isolation, and radiation could damage the brain in ways we don't yet know how to detect, let alone treat. None of this is secret in the conspiracy sense. The documents exist. Many are online. The silence comes not from erasing these concerns, but from placing them somewhere the public rarely looks. Buried in technical appendices, embedded in 400-page PDFs, discussed at conferences streamed to a few hundred specialists rather than millions of viewers. Space agencies live in a delicate balance. They need public enthusiasm to justify billion-dollar budgets. They also need to look unflinchingly at the worst things that can happen in deep space. These two needs are not enemies, but they do not always speak the same language. In press releases, Mars is described as challenging and demanding innovative solutions. In internal briefings, the same problems might be labeled mission-ending or not currently solvable. One version protects inspiration, the other protects lives. This duality shapes the way risk is communicated. A Mars surface habitat might be presented as a test bed for sustainable living off Earth. In technical design reviews, its main function is something more sobering: to buy enough time for crew to survive until a launch window opens to come home, if they are still healthy enough to travel. The public hears about in situ resource utilization, turning Martian ice into drinkable water and rocket fuel. Engineers quietly note that if those systems fail repeatedly in the early years, resupply from Earth will be impossibly slow, and backup options are limited to rationing, improvisation, and hope. Over the years, several official advisory groups have delivered assessments that are far less optimistic than the headlines that followed them. Some conclude that current radiation standards would be violated by a single round trip to Mars. Others warn that we do not yet understand how to maintain bone, muscle, immune function, and mental health on multi-year missions outside Earth's magnetic shield. These are not the dramatic revelations people imagine. No single report that says Mars is impossible. Instead, they are a chorus of cautions, each document adding a quiet line to a growing, uneasy song. Behind all of this lies a more terrestrial constraint: money. When Mars is discussed in public, budgets are often presented as impressive, even extravagant. Billions for rockets, billions for spacecraft, a sense that humanity is finally committing to its next great leap. Inside budget worksheets, the tone shifts again. Analysts see not one leap, but thousands of steps. Every system that keeps astronauts alive on Mars, life support, shielding, habitats, power, redundancy, is expensive. Every kilogram sent to the Red Planet is paid for many times over, in launch costs, development, testing, and decades of maintenance. Serious independent estimates of a sustained human presence on Mars, something more than brief flags and footprints visits, often climb into the trillions of dollars over the course of decades. And that assumes nothing goes terribly wrong. That number is not front-page material. It does not fit neatly into a tweet. But it quietly shadows every visionary animation of Martian cities. This is why timelines breathe. Publicly, Mars is always within a couple of decades. In the 1960s, it was the 1980s. In the 1980s, it was the early 2000s. In the 2000s, it slid gracefully into the 2030s. Now, as the 2030s approach, the language has shifted again. The first steps, preparatory missions, long-term horizon. Aspirational dates serve a purpose. They focus effort. They galvanize support. But inside mission planning offices, schedules are printed with another column: risk reduction. Before anyone commits crew to a 2 or 3 year journey, multiple precursor missions are needed. Cargo landers, robots to test resource extraction, long-duration habitation, and radiation experiments in lunar orbit or on the moon's surface. Each of these steps adds not months, but years. Launch windows to Mars open roughly every 26 months. Miss one because a system failed a test, a rocket suffered an anomaly, or a crucial technology is not ready, and the calendar lurches forward by more than 2 years. Multiply that by several dependencies, and an optimistic 2030 landing quietly becomes something closer to mid-century. The timelines are not lies. They are best-case scenarios under ideal conditions, spoken aloud, because the future needs milestones. But in internal risk matrices, beside each milestone is an unspoken asterisk. Assumes no major delays due to safety concerns. There is a deeper question beneath all of this, one that is rarely faced head-on in public forums: the ethics of going at all. Every astronaut today signs up knowing the dangers. Shuttle crews watch the Challenger and Columbia footage as part of their training. Risk is part of the job. But Mars is poised to introduce a different category of risk: slower, less spectacular, and more intimate. Not a sudden failure at launch, but a gradual breakdown of bodies and minds months or years away from help. What does informed consent mean when we cannot fully describe the long-term effects of chronic cosmic radiation on a brain that will also be coping with isolation, dust exposure, altered gravity, and untested medications? What responsibility do we have to crew members who might return from Mars with damage we cannot yet name? What duty do we owe to their families, who will watch them leave, knowing there is no emergency return, no quick rescue, only a trajectory that locks them into a world where help is always tens of millions of miles away? These questions are not ignored inside NASA. Ethics committees, bioethics panels, and independent review boards have all wrestled with them. Their conclusions are cautious. Many recommend tighter radiation limits. Some suggest that Mars crews may need to accept higher lifetime risks of cancer, neurodegeneration, or infertility than we currently allow. Others worry about precedent. Once we normalize sending people into conditions we know may shorten their lives, where does that boundary move next? Over the last few years, NASA's public language about Mars has begun to tilt, almost imperceptibly, under the weight of these realities. Where once the phrase was journey to Mars, it has become moon to Mars. The moon is increasingly framed not only as a stepping stone, but as a proving ground, a place to fail safely, to learn how often machines break, how humans cope, and what it really costs to sustain life away from Earth's cradle. Technical documents now speak more openly of high uncertainty and unknown unknowns. Public outreach leans more on phrases like preparing humanity and less on firm calendar dates. The agency emphasizes building sustainable systems rather than rushing to plant a flag. Even the rhetoric around Mars has softened, from settlement and colonization to exploration and presence, subtle linguistic shifts that acknowledge a truth engineers have always known. Living on Mars is not just harder than we think, it may be harder than we can currently imagine. None of this means Mars is off the table. It means the table is larger than the glossy posters suggest. Between the dream of walking on another world and the reality of surviving there lies a valley filled with engineering challenges, budget cliffs, ethical questions, and medical mysteries. NASA knows this valley well. It maps it in white papers and simulations, in budget hearings and late-night telecons. In public, it points to the distant peaks. In private, it studies the terrain in between, searching for a path that does not just reach Mars, but returns from it with something more than stories. Returns with lives intact, knowledge gained, and a future that justifies the risks we chose to take. So if Mars, the world we've been told is our backup Earth, turns out to be more like a slow-motion hazard zone, what then? The story of human spaceflight does not end on a dusty, radioactive plane under a thin pink sky. It bends, it branches, it finds other paths. When we step back from Mars and look at the larger canvas of the solar system, a different picture begins to emerge. One where our first great colonies may not stand on alien soil at all, but float, orbit, and machine scout their way through the darkness. We begin with the explorers that never need air. In the cold vacuum between worlds, robots do not get cancer. They do not miss home. They do not suffocate if a valve fails at 3 a.m. Their sleep is measured in standby modes and low-power states, not in restless human nights haunted by distance. Robotic explorers have walked where we cannot survive unshielded for even a moment. Curiosity and perseverance roam the Martian surface bathed in radiation that would slowly shred human DNA. Their wheels do not fear toxic dust. Their circuit boards can be replaced on the next mission, not mourned as lives lost. Machines have touched Venus, a place where the air itself could crush a submarine and melt lead. They have plunged into Jupiter's radiation belts, skimmed the surface of the Sun, flown through the nitrogen haze of Titan. They are immune to loneliness, to boredom, to bone loss, to the psychological gravity of knowing that home is a pale star 500 million miles behind you. Robots can fail in ways humans cannot survive, and we still call the mission a success. They can be designed to die for data. And yet, their greatest strength is not just endurance, it is multiplication. For the cost of sustaining a single human on Mars for a year, we can send an entire fleet of robotic craft to different worlds, moons, and asteroids, each gathering knowledge at the same time. Swarms of small probes could map radiation belts, scout ice deposits, even assemble structures in microgravity without ever needing a breath. If Mars is more dangerous than we hoped, robots are not a consolation prize. They are the advanced scouts, the first chapter of a much longer story in which humans follow only when we truly understand the ending. But where do those humans take their first real step? Not 140 million miles away, just 3 days. The moon waits for us like a training ground carved out of myth. It has no air, no magnetic field, and temperature swings that could shatter steel. In many ways, it is harsher than Mars, and yet, it is close, uncomfortably close, like a mirror held up to our ambitions. On the lunar surface, we can rehearse every nightmare we fear on Mars, with a safety net. Radiation shelters can be tested when an evacuation is still possible. Habitats can be buried under regolith, their air slowly cycled, their seals slowly stressed. We can watch how dust infiltrates machines, lungs and filters. We can learn what it means to live in 1/6 gravity for months, then years, and measure the quiet erosion of muscle and bone. If something breaks on the moon, we send a supply mission in days, not years. If someone becomes gravely ill, we at least have a chance of bringing them home. Lunar bases are not a detour from Mars. They are the simulator we cannot skip. We learn how to grow food in sealed environments, test in situ resource utilization on real alien rock, practice closed-loop life support that must work not for days, but for decades. We learn to live with the knowledge that the ground beneath us offers no mercy if our technology fails. And we do so with Earth hanging in the black sky as a reminder we are still within reach. From there, a harder question emerges in the silence. If Mars is this dangerous, is it even the right target? For decades, the image has been clear. Cities under domes, greenhouses stretching across ochre plains, children born into a low-gravity sunrise. But Mars is not the only storyline the cosmos offers us. Some scientists and visionaries look up, not out. They imagine giant orbital habitats, vast rotating wheels or cylinders where artificial gravity is generated by spin, where thick walls of water or regolith block radiation, where ground is a manufactured concept and down is whatever direction the cylinder decides. In these habitats, light is controlled. Seasons are programmable. Agriculture is not at the mercy of alien dust storms, but arranged in precise tiers, illuminated by sunlight, concentrated from mirrors, or by fusion lamps still to be invented. Instead of trying to terraform a dead planet, we terraform empty space. Others imagine generation ships, slow, self-contained worlds drifting between stars, where the destination is not a place, but a process, a vessel where those who board know they will never see the end of their journey, but their descendants might. In such a world, Mars and even the Moon become waypoints at best, footnotes in a much longer migration. These ideas sound like science fiction because for now, they are. They demand technologies we do not yet possess, but so did round-the-world voyages to people who had never seen a compass. To make any of these futures real, Mars colonies, orbital cities, interstellar arcs, we will need tools that border on the miraculous. We will need shields that turn lethal space into a gentle background hum, artificial magnetospheres, bubbles of electromagnetic force around ships and stations that mimic Earth's magnetic field, bending charged particles away before they ever reach human skin. We will need materials that are both light and nearly impenetrable to radiation. Layered composites, liquid hydrogen walls, water jackets that double as both life support and armor. We may not stop at engineering the ship. We may engineer ourselves. Genetic modifications that increase DNA repair rates. Alterations that change how our bones respond to low gravity, how our cells handle chronic radiation. Not science we can casually deploy, but science that, if used carefully, could make the human body less fragile in places it never evolved to be. These are not technologies for the next launch window. They are projects of generations, of a species deciding very slowly to become something that can live in space, not just visit it, which leads to an uncomfortable recalibration of our timeline. We like to imagine that Mars cities are just around the corner, that the first baby born on Mars might be someone already alive today. But when we match that dream against what we know about radiation, about partial gravity, about the absolute fragility of complex medicine far from Earth, a different estimate starts to form. Mars may still be our future, just not our near future. The 21st century may belong to precursors, robot fleets, lunar laboratories, orbital way stations. The 22nd century, or the one after, that may be when true Martian cities become realistic, backed by technologies and biological understanding we can barely sketch now. In the meantime, other destinations quietly raise their hands. Venus, with its hellish surface, hides a surprising niche. 50 kilometers above its inferno, the atmosphere becomes more Earth-like in pressure and temperature. Some scientists imagine vast floating habitats in the Venusian skies, sailing on dense clouds of carbon dioxide, basking in an almost Earth-strength gravity, and wrapped in a thick atmosphere that offers natural radiation protection. No one is moving in tomorrow, but as Mars reveals its teeth, Venus's clouds no longer seem entirely absurd. Asteroids, too, shift from rocks in the dark to potential lifelines. Mining water ice locked inside them could provide rocket fuel, radiation shielding, even building material. Hollowed-out asteroids, spun gently for artificial gravity and wrapped in protective layers of their own rock, could become the first true space towns, remote, rugged, but resource-rich in ways Mars soil can never be. When we spread our map out fully, Mars is no longer the single red dot at the end of the line. It becomes one of many options, each with its own dangers, its own bargains. And in that complexity lies something important. Letting go of the idea of a quick, easy Mars colony is not the same as abandoning the dream. It is, in a strange way, how we keep it alive, by being honest about the hazards, radiation, dust, gravity, psychology, medicine. We buy ourselves something precious, time to prepare, time to test on the moon, to perfect our machines, to build our orbiting experiments, to decide together what risks we are truly willing to take. Mars does not have to be the next step to remain a step. It can be the distant mountain we see on the horizon of our species' journey, a goal we circle towards slowly, through failed prototypes and brilliant robots, and quiet nights on a lunar base where astronauts look up at a tiny red star and know, someday, but not yet. Between here and there, the universe is generous with alternatives. We may ring Earth with habitats before we ever walk Martian streets. We may dive into the clouds of Venus, carve homes into asteroids, send slow ships toward Proxima Centauri. Or we may do all of these in a branching, messy, unpredictable expansion that looks nothing like a straight line to a single planet. In every version of that future, Mars still matters. Not as our emergency exit, but as a mirror held up to our limitations and a challenge to surpass them. The danger of Mars does not close the book on exploration. It turns the page and reveals that the chapter we thought was next might in fact be several chapters ahead. And that might be the most hopeful thing of all. We drift away from Mars now, not in distance, but in perspective. The red planet shrinks behind us, a rust-coloured ember hanging in the dark, and with it, the dreams we've cast onto its surface for generations. For a long time, Mars has been our mirror, a place where we projected our hopes for adventure, escape, even rebirth. But as the data piles up like sediment in an ancient Martian crater, a quieter truth settles in. This world is harsher, more complicated, and more unforgiving than the posters and headlines ever suggested. The radiation that needles through your cells, the dust that seeps into every seal and lung, the gravity that slowly unthreads bones and hearts, the isolation that stretches the mind thin. Each of these is not a footnote. They are chapters in the story of why Mars may already be too dangerous for the kind of thriving human colonies we imagine. NASA knows this. The engineers know it. The medical officers know it. Buried in technical reports, in conference talks, in cautious wording, is a message. Mars is not just far away. It is fundamentally different from the home that built us. But recognizing that is not surrender. It is the beginning of wisdom. Choosing to see Mars clearly does not mean turning our backs on it. It means walking toward it with our eyes wide open, unblinded by glossy concept art and quick headlines about cities on Mars by 2050. It means trading in the fantasy of easy colonization for the far more interesting, far more demanding reality of gradual, fragile, hard-won presence. Between those two visions lies the work. Better radiation shielding, perhaps buried habitats, or magnetic deflectors not yet invented. Smarter life support that recycles every molecule of air and water with ruthless efficiency. Medical science that can keep human bodies functional in low gravity for decades, not just months. Psychological tools that turn isolation from a threat into a tolerable, even meaningful part of the journey. None of that appears by wishful thinking. It arrives molecule by molecule, paper by paper, mission by mission. Transparency about the risks isn't a brake on exploration. It's the engine that keeps it honest. When we admit that Mars can kill us in a dozen subtle ways, we free ourselves from shallow timelines and marketing slogans. We can ask better questions. Not, how soon can we live there? But, what does living even mean in a place that's hostile? Not, how fast can we go? But, how long can we endure? Hype burns bright and dies quickly. Reality, even when it's unsettling, burns steady. It lets planners design safer missions. It lets the public decide, with full knowledge, whether this is a risk worth taking. It treats exploration as a shared choice, not a sales pitch. And maybe that's the hardest part to accept. Mars is not a project for a single administration, a single CEO, or a single lifetime. It is a thread that will be passed from one generation's hands to the next. The first crews who orbit Mars, or touch down for a few cautious weeks, will not be building cities. They will be writing the preface. The people who follow, decades, even centuries from now, may be the ones who attempt something like permanence. Or they may decide that Mars is better as a laboratory and a frontier outpost, not a second Earth. Our role is not to finish the story, but to begin it with enough humility that someone else can continue it safely. From this long view, Mars stops being a promised land and becomes something more interesting. A test of how patient we are willing to be, how honest, how careful, whether we are capable of exploring a dangerous world without pretending it is gentle. If you've stayed with this journey through dust storms, broken bones, and the quiet weight of distance, take a moment to pull back even further. Look at that tiny red point in the sky above, wherever you are right now. Bedroom, bus, night shift, distant country. In the comments, tell us where you're listening from on Earth's surface, this one small oasis in the dark. It's a reminder of what we're risking and what we're trying to understand. If this helped you think about Mars a little differently tonight, tap like so others can find it, and subscribe if you'd like more slow, careful explorations like this while you drift off to sleep. And if you want to go one step further, you can join our YouTube membership to support the channel, completely optional but deeply appreciated. For now, we leave Mars where it is, cold, distant, and waiting, not for conquest, not for escape, but for the slow, deliberate work of a species just beginning to understand that some worlds are not tamed in a decade, or a career, or even a lifetime. They are approached cautiously, honestly, and together, across generations.